and orthonormal basis for L2 of SU2. So offshoot is the following. So this is an L-dimensional representation. So given any L-dimensional representation as M and N are varying, I have got that many functions. So offshoot of this is L2 of SU2 has a basis consisting of, I have down E, N, I, J, N is a half integer, I, J are varying from minus L to L. So this space will have such a basis, and the condition of equivariance will imply, so you may ask what are these spaces? H lambdas, so D on En Ij span of the space En Ij, where J are varying, is really restricted to this space, is, as I said, some scalar times identity. So this will have such a basis. In this example, for Sn case I wrote down some H lambdas. So in this case the lambda parameters are this half n, and H lambda spaces are really given these objects. Now we write down the condition that D commutator generator, so SU2 is generated by two numbers, maybe two complex numbers. So D commutator alpha and are bounded, and if you represent this data in a diagram, and it is this part which is complicated in the general situation. So I want to represent these quantities in a picture. Alpha is an element in SU2. It is, I am looking at L2 of R, there I represent alpha, and I have constructed an element D like that. I consider the commutator alpha. Yes? Is this understood or winning now? Am I leading myself into frustration? That is the question. Have you understood that? No? Okay, that is not very difficult. So, can I get into it? Alpha Martin is my name. So can I symbolically do it? Okay, so in S3, L2 of S3 has got a basis like that. That is clear? I mean, that's what I said. I have not done anything. All I am saying is that alpha and beta are elements of S3, which is SU2, alpha and beta. So what are these? These are actually, these elements are elements of M2 of SU2. You understand that now? Meaning I have just asserted, I have not verified, I said it can be done. And then alpha and beta are the functions here. What are these functions? If I take a matrix, say U11, U12, U21, 2, 2. This is a matrix from SU2. I look at this entry. Is that a continuous function? That is a continuous function. Therefore, if it is a continuous function, I can multiply a square integral function by that. So, this continuous function is represented as bounded operator here. So, I call that alpha. Similarly, I define beta. So, I have got two operators.
Coefficient function.
Yes, these are the coefficient functions. And then, this condition that they are bounded, of course, it requires computation. If I do not compute, I do not know how those scalars are. So I want to represent that condition, and that's how our argument basically goes. I want to explain this argument because once it is understood, it can be explained, meaning applied in any concrete situation. In any concrete situation. I am more or less certain that it can be done for any of these things. I am looking for amplified proof, that's why. So let me represent this. So these levels are n. Okay, this is n equal to 0. N equal to 0 to n plus 1 is 1. That means the representation is one dimensional. So n equal to half to n plus 1 is 2. Representation is two dimensional. N equal to 1. This is three dimensional. So what are these objects represent? They represent the various values of I. D is defined on these spaces. E and ij's are bases of L through SU2. How many are there? For any n, there are n plus 1 i's, n plus 1 j's. If I have any of those i's fixed, this is a space. And on that space, D is given by this quantity. Therefore, you should imagine on this point, these dots represent ni's. On this point, you have this space Ct. You can imagine on this point that space Ct. More elaborate picture is possible and helps to understand things better. But for this is enough. So think of at this point, points represents ni's, and on this point you have this inverse space. If I call it H N I. Now, you write down the condition that d commutator alpha and d commutator beta are bounded. That condition boils down to the following set of inequalities. If you take difference between two such numbers on this half, difference between any two such numbers are bounded. This is a consequence of these two quantities bounded. At the same time, difference between two such numbers are bounded. I said that it will boil down to growth rates of these numbers. We are eventually interested in how fast these eigenvalues are growing. These are the eigenvalues of t. Therefore, you can see very quite easily that these quantities are actually bounded by why? Pick any level n and pick an index I here. Okay? I want to show this is C of n. Okay, fine. So I take certain steps. Oh, sorry. These quantities are, these differences are bounded, these differences are bounded, and difference along this line is also bounded to this central line. Start with any vertex. Take certain steps, come here and go there. Therefore, any of this is actually n away from this vertex, and that shows that these quantities are less than or equal to Cm. And then, of course, you know that on a space of dimension 2n plus 1 square, it can be at most n. Therefore, this mod b alpha, this is finite, will imply finiteness of this, and for that your alpha must be greater than 3. So this is the argument for SU2, and of course as you make it for SUQN or SUNs, things may get complicated as Martin asked. We prove it for SUQN, which is same as dimension SUN. We prove it for SQN, it is same as dimension SN. For Kunz algebras, these are infinite, that is expected. For non-commutative torus, it is n as you expect, so on and so forth. So, mid task is really computing it for various groups or spheres. One can do a case-by-case argument, but I do not want to do that. Somebody, if he wishes to do it, can do it. Yeah, that is possible. A case-by-case argument is possible. So that's it. Oh, I see. There are various variations possible. I talked about one variation, that is throwing in the sign of the operator D. Other variations are also possible, which are, of course, considerably complicated. Instead of computing this AHD and looking for finiteness of trace mod d power minus alpha, you can straight look for AHS, such that this is the freedom model, and best possible alpha such that F commutator A in the Schatten idea. Unfortunately, one has tried to compute this also for Kunz algebras. In that case, the result becomes 0. Still, it is not really as interesting or uninteresting like this infinity. So, this is one variation possible. Another variation that is possible is allow multiplicities for H instead of this. So, you have a fixed H row. Maybe you can allow these representations and allow more larger classes of D. That is another possibility. But again, it becomes more and more complicated with the calculation. Oh, I should also tell you one more thing, that this quantity for C of G is less than equal to dimension of G. That inequality is obvious. That is not very difficult. But the other one are very easy.
For the other inequality, what you don't know?
For the other inequality, we do not yet have a proof. I believe one can